Okay, thank you everyone for coming today. I'm Shaiful Chowdhury. I'm a PhD candidate at this department, and today I'm going to present our paper GreenBundle. I'm going to present it at ICSE 2019 in May at Montreal. So we have Abraham Hindle, my PhD supervisor, Rick from University of Hawaii, then Takumi, Ken, and Yasu from Kyushu University, Japan. So motivation, like why I'm doing this. So the first question I asked like few years back was, do people really care about my research? Like, so in summary, is my PhD research really important? I think many PhD students ask this question every now and then, like by themselves. Luckily, one day I was at IKEA and I was waiting to talk to a customer agent. And then there was a customer in front of me. The customer agent asked the customer, "Sir, did you install our app?" And the reply was, "No, they all kill my battery." So I was like, yes, my research is important. And then I was watching a movie called Eye in the Sky with my family. So there was a Beetle drone that the military people were using to monitor a terrorist activity. And then at a very sensitive moment, the Beetle drone was out of battery charge and they could not record it anymore. So I was telling my family, see, that's what I do for my PhD. And then Microsoft Surface Pro, like lots of users complained recently, like the battery was dying much faster than the expected time. Then Microsoft investigated that issue, and what they found was, it was no hardware issue. It was a software bug, which we call energy bug. Then they fixed it, and then it was resolved. So yes, software energy efficiency is very important. So what is software energy consumption anyway? So when I tell people about my research, the first question they ask is it not the hardware components that consume energy? The answer is yes. But then who controls those hardware components? Software, right? You can access the components efficiently or inefficiently. So that's why our software energy efficiency comes in. But why I am focusing on smartphones for this research? Like according to eMarketer, the number of smartphone users will exceed 4 billion by 2020. And according to many recent surveys on smartphone users, the users reported that they desire longer battery life than any other non-functional features. The problem is, the way computing power is increasing, battery technology is not improving accordingly. So, which means you can do more complicated tasks nowadays with your smartphones, but then at the same time, your battery dies faster. Which means we need to write energy efficient code, or we need to develop energy efficient software. So in last 5 years, I would say there have been lots of work on software energy efficiency. And one of them was, for example, energy efficiency of Java collections. So this paper provided a list of recommendations for scenarios like, should you use array list, for example, instead of linked list to save energy, things like that. And this paper actually won the ICSE Distinguished Paper Award for this work. And then I also did some work on energy efficiency. One of them was comparing HTTP 2's energy versus HTTP 1.1's energy. There are other works like, if you have code smells and you fix them, does it improve software energy? So all of these kind of work. But the problem is, another research by Shahin in 2016, I think it's a journal paper in Empirical Software Engineering, they found that all of the previous work, what they do is they develop a benchmark app and say you are doing that Java collection thing, you replace your array list with a linked list and measure the energy. So that's how they find things. But whatever you find from the benchmark app, most of the time you don't see the same impact on real world app. So, for example, if you use a linked list instead of an array list, and you can claim that, energy gain is 200%. So it sounds big, But the actual difference is maybe 2 or 3 joules, which is quite low when you go to real world apps. When you use the app, the energy consumption is say 500 joules, then saving 3 joules doesn't mean anything. So what it means is, what it indicates is, we need higher level changes, like design level changes, so that the software accesses the hardware components efficiently. That's what we do in this paper. And I want to start this paper with this question. So there are 3 scenarios here. The leftmost one shows how on-time processing works, like the normal app, the way you write software. So you click on a button and you immediately process it, right? So that's what I call on-time processing. For example, job 1 came, you immediately completed job 1, which is C1. Then after some time, job 2 came, you completed job 2. But on the right hand side is dropping. So dropping, the idea of dropping and bundling is, you don't process an event immediately. You wait for a period of time. Say your waiting time is 0.1 second, right? And then when you store all the incoming events, and when the waiting time is over, then you process the most recent event. Why? Maybe there are some applications where if you process the most recent event, you don't have to process the previous events. For example, the weather app, right? So like if you have 3 weather data, you might not care about the previous 2 data. You just want to show the most recent one. So this is just an example. So this is dropping, right? Bundling is very similar to dropping. It also has a waiting time. When the wait time is over, you store all the incoming events. And when the wait time is over, you process all of them together, right? So you don't lose anything. Maybe you have some latency, that's it. But you don't lose any task, you process all the tasks. So the question is, which one do you think would be most energy efficient? Any guess?
Dropping?
Yeah, that's obvious, right? Because you only process, out of 3 events, you only process 1. So I asked these questions to many of my friends who are in computing science, and all of them said dropping, and they're right. But if I ask, which one would be more efficient between the first 2? Because the first one process all the tasks immediately, right? The second one process all the tasks. No difference. It doesn't drop anything. So which one would be more energy efficient? Or the question is, would there be any difference? Yeah.
I think bundling is more efficient.
Why?
Because the way you're drawing it here is just like memory coalescing, so you get less accesses to memory when you get more chunks from memory at once. But that's how I see it.
Your first answer is right. Bundling is more energy efficient. But the second answer is, complicated.
Okay.
But also there is another complication, which is when you do bundling, you have some overhead, like waiting time, another thread, and all this stuff. So we'll see what happens in this paper. If it's more energy efficient, that's great, because we are processing all the events and we are saving energy. But then the question is, how much? Okay, so our contribution in this paper is, we want to help developers at design time before they start coding. So high level change. For that, we propose a modification in the model view presenter architectural pattern. And in this paper, we only focus on Android apps. But later we will show that our implications might have significance on, like impact on other platforms as well. So how MVP works? So there are 3 components in model view presenter pattern. So it's good for separating your concerns, like you have less dependency among the classes. So the model class or component deals with only data and data source, right? For example, you are interacting with the database, or I don't know, you are communicating with a remote source, something like that. So model deals with that. View only deals with your UIs and their interactions. So that's how you separate the concerns. Whereas presenter deals with business logic, like what should we do? That's what the presenter decides. For example, when a user clicks on a button, or provide some values to save, it will notify the presenter, and then the presenter will notify the model that, hey, something is changed, you should change your state. So that's how MVP works. What we propose is we want to modify this presenter component so that it can do the bundling and dropping tasks. So what it would do is it would not process immediately, it will store them, and if it's bundling, it will then process them all in a batch. If it's dropping, it will only process the last one, last event. So what is an event? An event can be anything: a database update request, a packet transmission request, or a view update request. So again, the bundling presenter will process all the events together, whereas the dropping presenter will only process the last one. In this paper, we only deal with view updates, not like packet transmission or those things. So methodology. To understand the energy gain or how it works, we first developed a benchmark app. And then, as I said, benchmark app might be misleading sometimes. So that's why we evaluate our findings from benchmark app to real world apps. And then we also try to understand why bundling or dropping is more energy efficient, if they are more energy efficient. And then we also add one more analysis, which is if bundling and dropping saves energy, that's good, but is it bad for the maintenance cost? Like, does it make the code complicated so it's become difficult to maintain in the future? Okay. So here is the benchmark app. As I said, see, we have a model component which is composed of some emitters. You can have one or more emitters. Emitters means your data source, like the source that emits. So you can have one or n times n number of emitters. Then you have the emission object, which is whatever the emitter emits. So in our case, it was very simple. It was a simple string object. That's it, some kind of string. So because we wanted to keep the benchmark app as simple as possible so that we don't have too much overhead. And then we have emitter queue, which is a Java priority queue, like when the events are generated, in what order they should be emitted, and which comes from the distribution component, which can be uniform distribution or Poisson distribution, whatever you want. You can plug in your own distribution formula if you want. And then we have the presenter components and three types of presenters: dropping, bundling, and no bundling. So no bundling means the normal presenter, the on-time processor. So you can decide on runtime how many emitters you want, what distribution you want, and what kind of presenter you want. So with this benchmark, we can compare bundling, dropping, and normal. And the good thing is, we have shared the source code of our bundling and dropping presenters. So if you are planning to apply this into your app, you can just plug in that presenter. Now, in order to run the benchmark app to measure the energy consumption, we needed to write some automated scripts so that it opens the app, provide the inputs, and run the app, right? So I used ADB shell scripts, which is very simple. Now for energy measurement, we use the GreenBundle test bed. GreenBundle is really famous. Like there are lots of energy papers which used GreenBundle, but this paper is a bit different. Like we use two different kinds of GreenBundle to see how if our results are true across different phones. So the first one is Samsung Galaxy Nexus, which is very old. And then the next one is, I think it was Asus Zenfone 2, which is more recent. So if we can see our results are similar across these two different phones, we can say it would be true in other phones as well. Okay, so the two research questions using the benchmark app we answer are: what is the impact of the number of event sources and event generation rates on software energy consumption? Which means if you have more and more event sources or higher and higher event generation rate, does it increase the energy? If yes, how much? And then the next question is, can bundling and dropping events help in saving energy? Okay, so here is the answer for research question 1. So as you can see, the x-axis represents the event generation rate. So for example, 4 means per emitter you generate 4 events in a second on average based on your distribution. Y-axis is the energy, and as you can see, I have a number of emitters there. So this one is for when the number of emitter is only 1. You have only one data source. And then what would be your energy based on the event generation rate? So although it does not look like linear because it's not a complete linear scale, but it's almost linear when we calculated the correlation coefficient. So the finding is obvious. Like if you increase the number of emitters and or the event generation rate, you will have linear increase, almost linear increase in energy consumption. But how much? If you even have only one emitter, one data source, the energy consumption can go up to 38%, which is huge, right? And modern apps, modern applications, they have so many event sources. So we need to do something to save energy here. So the question is, can bundling or dropping help? So I have considered this for all the scenarios, like when the number of emitters is 1, 2, 4, 8, 32, 64, like that, like power of 2, but I am only showing 2. So as you can see, the top one is no bundling, like normal processing. Event comes, you process immediately. And the bottom 3 is for dropping, as you guessed, like they're the most energy efficient. But when you drop or when you bundle, you also need to say for how long, would be your waiting time, right? So here I showed 3 scenarios. One is 0.1 second, which means you don't even see it. You don't even see the difference, right? Another is 1 second, because it is reported that the user acceptable time for interacting with the UIs are 1 second. So that's why we also considered 1 second. And then the half of 1 second, which is 0.5. What is interesting is the difference between bundling and dropping in saving energy is not that much, right? But the difference with no bundling is huge. So it's interesting because with bundling you are processing everything. With dropping you are processing only the last one. Still their energy consumption is very similar. Yeah.
Can you use your hands and show us what are the bundling results and what are the
Okay.
dropping results?
Okay. So this is no bundling, right? This is dropping at 1 second. Like you wait 1 second and then you process the last event. Of course you save the most energy. Like if you wait 1 second, then waiting 0.1 second, right? And this is dropping for 0.5. Then this is dropping for 0.1. And similarly these are for bundling, right? So the idea is if you wait more to process, you save more energy, right? So I think it's interesting because it tells us that with bundling, we can save energy, like which was a bit surprising to many people because you are processing all the events. And why this is so exciting? Because you can save 25% energy for this case when your waiting time is only 0.1 second, which means the user will not notice anything. You are processing all the events and you still save 25% energy. So that's the complete win. But as I said before, like, can we see similar observation in real world apps? So for that, we selected 4 apps from the F-Droid repository. Like, not more because it's hard. I have to literally understand the source code totally and then refactor the source code with my bundling presenters or dropping presenter, right? So I selected 4 apps and then we refactored those apps with bundling and dropping. And these are the 4 apps, sensor readout. And I tried to have them so that they are different in their line of code and number of classes. So we can observe like how bundling affects something, an app that is big versus an app that is not that big, right? So for example, for sensor readout, we have 56 classes, like Java classes. Whereas for Angular, we have 4 Java classes. And these are the apps. So for example, this is sensor readout. If you open this app with a sensor, like which is gyroscope, in this case, it measures the energy, not the energy, I mean the sensor data, and shows all of them. So this is a paint app. So just consider this app, like it's a paint app, which means user will spend a lot of time with this app. If you can save energy with this app, that's very important. And then we have other 2 apps. One is Angular, like for distance and angle measurements, and this is Color Picker, a simple app. If you just swipe those bars here, it will show you the color for that values, RGB, and the hexadecimal values. So this is a simple app. And I got very similar observation for all the 4 apps, but I'm showing only one here because they are very similar. And I selected acrylic paint. And as I said, I used 2 different phones.
Quick question about the dropping. I'm assuming that paint is supposed to be interactive. So is like the last place where your finger is the only one that's colored for dropping, or?
So it depends on your waiting time. If it's 0.1 second, I tried with 0.1 second, you don't lose anything.
Yeah, but for 1 second they would.
Yeah,
Okay.
so which means for 1 second it would not make much sense.
Okay.
So it would be on the users, they will select what waiting time they want, right?
And this graph is for yes, 0.1.
Acrylic paint. You want this graph.
No, sorry.
Okay.
Good. Yeah.
Okay.
I have a
Yeah.
question. So those apps had already existing implementations, and you modified them.
Yeah.
Is that using that diagram you had, but like your framework? Because
Yeah.
that was for your default, your benchmark app, right? You implemented it using this way to configure it.
Yeah.
But how easy is it to change things in an existing app to use those different?
Okay. So for the developers, it would be extremely easy. Say you are the developer for this app, right? So you know where exactly you are doing the processing. You can just copy my presenter code and just, I don't know, it would take 10 to 15 minutes to apply the whole thing. I was not the developer, so it took me some time to understand where things are going on. But then I would say for the first, for this one, and this one, I didn't take more than 1 hour to complete everything. But this one was difficult to understand, the acrylic paint. Yeah. So this is the acrylic paint. So now think like if you apply bundling, you are not losing anything, right? You are drawing the whole thing, and if your waiting time is 0.1 second, you are not even noticing the delay, right? So if you can save energy with bundling and waiting time 0.1 second, that's a complete win. So the top 3 lines are for GreenMiner 1, which is with Samsung Galaxy Nexus, and these bottom 3 are for Zenfone 2. So the flat line is no bundling, normal one, the original app. Now as you can see, with more waiting time, we can save more energy. But this is 100 millisecond here, which is 0.1 second. And you see the gain here. And that was 12% saving. So you just saved 12% energy without losing anything. Almost no latency, and you didn't lose anything because it was with bundling. Okay, the next question we asked was, there are some scenarios where users complain about an app. Can we address those concerns if it's related to energy with our bundling and dropping? So we selected, for this study, we selected the sensor app. Why? Because out of 4, it was the only app that was available on Google Play, and it was downloaded more than 50,000 times. So I would say it was famous, and the rating was even 4.3 out of 5. But we observed by reading the user comments some dissatisfaction. One user was confused why the sampling rate was low. because by default the sensor readout app samples 10 data per second. The user wanted more. But if you have, say for example, 30 samples per second, don't you think it would harm your energy consumption? How about we sample more data but with bundling? So that's what we are going to show. Okay, so here is the sensor readout app. I tried with different number of measurements, which is samples per second, 5, 10, 20, 30. Here is the default one, right? When 10 measurements per second, there is no difference between bundling, dropping, and the no bundling. But when you sample 20 per second, the original goes there. But bundling is here. So you just saved, and that is with only 0.1 second waiting time. So almost no latency. So you just save 36% energy with bundling. So you satisfied the user without harming the energy. Okay, now the big questions, like Corinne said, maybe because of the memory access or something, like the question is, bundling does the exact amount of work like no bundling. Then why does it save energy? Dropping is obvious, it does less work, that's why it saves energy. But what is the case with bundling? So our assumption was less context switches with bundling. So when an event comes, you need at least one user space CPU slot to process that event. And with that, you also need at least one kernel space CPU slot. So at least 2. But if you do bundling, like a batch processing, you might be able to do more work with one CPU slot, like user space CPU slot. You don't need the kernel CPU slot every time for all the events because you are processing them in batch. So if you do that, you are reducing context switches. That was our assumption. And then we found it to be true. Like we calculated the number of context switches. And here is the bundling dropping time. And as you can see, with more bundling dropping time, you have less and less number of context switches with bundling and dropping. And in one of my previous work, Green Scalar, that was published in Empirical Software Engineering, I showed that number of context switches is linearly correlated with your energy consumption. So we now know why bundling is more energy efficient than no bundling. Now the last question is, okay, so far all good. You are saving energy without affecting the latency, right, with bundling. But does it hamper your maintenance cost? Because if it does, then the developers might not be interested because it will harm the long-term maintainability of your app. So then we calculated the number of lines that we had to modify for each of the real world apps. And for no app, we had to modify more than 100 lines. It was like around 60 lines of code, that's it. And you don't have to write the code. The code is there. You just have to refactor it with our provided presenters. But unfortunately, number of lines sometimes don't mean anything, right? Like you can just inject few lines of code, and with that you can have a lot of dependencies among the classes, which is really bad. So to measure that, so that's what I was talking about, dependency. So to measure that, we use the decoupling level metric. It was published in XC 2016. So one of my co-authors in this paper was there. And so if you have a source code for an app, you calculate the DL score for the source code. If your score is 100, which is impossible, I would say, is the best case. There is no dependency among the classes. If it's 0, that's the worst case. Like it's a really, really bad code. Like all are dependent. So you cannot modify any class without modifying others. So that's bad. And they have shown that DL metric is really reliable. For like it outperformed other previous methods. So that's why we selected this score. And here is the results for the 4 apps. So for Angulo, for example, this is the original score for the original app, 68%. I would say that's not bad. With bundling, it's only 69. So the difference is 1, right? And we don't show dropping because it's very similar to bundling, because they are kind of the same presenters. Color picker, it was really bad from the beginning, 17%, and it stayed 17%. For acrylic paint with our presenters, it actually improved, like from 88 to 82. So in any case, it was never more than 10. And according to the DL paper, they said if the difference is less than 10, that's not significant. You can just ignore this. So what it means is we did not hamper the maintenance cost of those apps by applying our presenters. So the final message is we saved energy with our pattern, like modified MVP pattern, without affecting the latency and without affecting the maintenance cost. So summary is we proposed a design time pattern with a modified MVP. We showed that we can apply them to real world apps, we can save energy, and we say that's a win-win because we don't lose anything if our bundling time is 0.1 second. Now why this work is important? Because it is the first work on that topic, and like what can we do in design time to save energy, and we showed that a simple architectural choice can make a huge difference, which means we should focus on this area even more, like let us do more work about app designing to save energy. Thank you.